In the grand theatre of public discourse, carbon dioxide has been cast in the role of the ultimate villain. We are told, with increasing urgency, that this invisible gas is the primary driver of a looming climate catastrophe, a pollutant that must be scrubbed from our atmosphere at all costs. This narrative is presented as a settled fact, a conclusion endorsed by an overwhelming consensus. Yet in the world of science, true progress often comes from questioning the consensus, from looking at the data with fresh eyes and daring to ask whether the story we are being told is the whole story. The case against carbon dioxide is not as simple or as certain as many would have you believe. It is a complex issue filled with nuance where other powerful factors are often overlooked. This essay seeks to explore a different perspective. It is a perspective that acknowledges the fundamental physics of our planet but challenges the singular focus on CO2 as the sole controller of our climate. We will journey into the science of sunlight, the transformation of our planet's surface, and the physical limits of how gases interact with heat. We will see that while CO2 plays a role in the Earth's energy balance, its influence may be more modest and more complex than the headlines suggest. It is time to step back from the alarm and examine the evidence with a calm and open mind, considering possibilities that the mainstream narrative often dismisses or ignores entirely. The debate is not merely academic. It has profound implications for how we live, how we power our societies, and how we view our relationship with the natural world. By focusing so intensely on this one molecule, are we missing other, more significant changes we have made to our planet? Are we ignoring the direct, localized ways in which human activity alters our environment, such as the vast expansion of cities and agriculture? These are not small questions. They demand that we look beyond the simplified models and political sound bites to understand the intricate dance of energy and matter that shapes our world, a world where CO2 is also a fundamental building block of life itself. Therefore, let us begin this exploration not with a conclusion already in hand, but with a spirit of inquiry. We will consider the arguments of respected scientists who have raised legitimate questions about the prevailing climate orthodoxy. We will differentiate between the very real phenomenon of warming in our urban centers and the broader, more complicated picture of global climate. Ultimately, the goal is not to deny reality but to enrich our understanding of it. We must ask whether carbon dioxide is truly the villain it is made out to be, or if it is a misunderstood component of our biosphere, essential for life and perhaps less powerful in the climate system than we have been led to believe. To understand our planet's climate, we must first understand the energy that drives it, which comes almost entirely from the sun. The sun bathes our world in a constant stream of energy, but this energy is not all the same. It travels to us primarily as shortwave radiation, which includes the visible light our eyes can see, as well as ultraviolet and near-infrared light. These short waves of energy pass through our atmosphere with relative ease, much like light passing through a clean window pane. The gases that make up our air, including nitrogen, oxygen, and even carbon dioxide, are largely transparent to this incoming solar radiation. The energy's journey is not complete until it reaches the Earth's surface. Once this shortwave radiation strikes the Earth's surface, be it soil, water, or a blade of grass, it is absorbed and the surface warms up. A warmed object, however, does not simply hold on to this energy forever. It must release it. The Earth radiates this absorbed energy back out towards space, but it does so in a different form. Instead of shortwave radiation, the planet emits longwave radiation, also known as infrared or heat radiation. This is the same kind of energy you can feel radiating from a hot pavement on a summer day or from a warm stovetop. This transformation from incoming shortwave to outgoing longwave radiation is the fundamental process at the heart of our planet's energy budget. The difference between these two types of radiation is critical. While our atmosphere is mostly transparent to the sun's incoming shortwaves, it is not as transparent to the Earth's outgoing longwaves. Certain gases in the atmosphere, known as greenhouse gases, have a molecular structure that allows them to absorb specific frequencies of this outgoing long-wave radiation. When they absorb this energy, they vibrate and then re-radiate it in all directions. Some of this re-radiated energy goes out to space, but some is directed back down toward the Earth's surface, effectively slowing the rate at which the planet cools. This process is the famous greenhouse effect, and it is what keeps our planet warm enough for life to exist. Without this natural greenhouse effect, the Earth's average temperature would be far below freezing, a frigid and inhospitable world. Molecules like water vapor, which is the most significant greenhouse gas by far, as well as carbon dioxide and methane, act as a crucial atmospheric blanket. They trap just enough of the outgoing heat to maintain a stable and life-sustaining climate. The entire climate discussion, therefore, is not about the existence of the greenhouse effect, which is undisputed, but about the precise sensitivity of the climate system to changes in the concentration of one of its minor components, carbon dioxide. Understanding this flow of energy is the first step to seeing the bigger picture. The Earth's surface, the very place where solar energy is absorbed and re-radiated, has undergone a radical transformation over the last 2 centuries. Before the Industrial Revolution, the landscape was dominated by natural ecosystems. Vast forests, sprawling grasslands, and pristine wetlands covered the continents. These natural surfaces have specific thermal properties. They are generally dark and moist, and through processes like photosynthesis and transpiration, they interact with solar energy in a way that moderates temperature. Trees provide shade, which keeps the ground cool, and the process of transpiration releases water vapor into the air, which has a cooling effect, much like how sweating cools our skin. This was the Earth's natural state for millennia. However, the rise of modern civilization has dramatically altered this landscape. We have cleared immense tracts of forest and ploughed under native grasslands to make way for agriculture. While farming is essential for feeding a growing population, this conversion changes how the land interacts with sunlight. A field of crops has a different color, texture, and moisture profile than a mature forest. Furthermore, the machinery, fertilizers, and irrigation systems associated with modern agriculture create their own distinct environmental footprint. This large-scale conversion from natural, self-regulating ecosystems to human-managed agricultural lands represents one of the most significant physical changes humans have ever made to the planet's surface. Even more profound has been the explosion of our cities. What were once small towns have grown into sprawling metropolises, replacing soil and vegetation with concrete, asphalt, and steel. These artificial materials have thermal properties that are vastly different from those of the natural world. Asphalt roads and dark rooftops are exceptionally efficient at absorbing solar radiation, much more so than a grassy field or a forest canopy. They soak up the sun's energy all day long and then continue to radiate that heat back into the environment long after the sun has set. This is a fundamental alteration of the local energy balance, driven by the very materials we use to build our modern world. This shift from a green and moist surface to a dark and dry one is not a minor detail in the climate story. It is a central plot point. We have systematically replaced surfaces that had natural cooling mechanisms with surfaces that are designed to absorb and retain heat. Think of the difference between standing barefoot on a lawn versus a paved parking lot on a sunny afternoon. The parking lot is dramatically hotter. Now imagine that effect scaled up over millions of square miles across the globe. We have fundamentally changed the thermal character of the Earth's land surface, creating localized heat zones on an unprecedented scale, a phenomenon entirely separate from the composition of the global atmosphere. The direct consequence of replacing natural landscapes with artificial materials is a well-documented and undisputed phenomenon known as the urban heat island effect. As the name suggests, our cities function as islands of intense heat, often registering temperatures significantly higher than the surrounding rural areas. This is not a theoretical model, it is a measurable reality confirmed by countless studies and satellite observations. On a calm, clear night, the temperature difference between a city centre and a nearby countryside can be as much as 10 degrees Celsius or 18 degrees Fahrenheit. This localized warming is a direct result of the choices we have made in how we design and build our urban environments. The primary cause is the absorption of solar radiation by man-made surfaces. Concrete sidewalks, brick buildings, and asphalt roads act like giant heat sinks, absorbing the sun's energy during the day and slowly releasing it at night. This prevents cities from cooling down after sunset at the same rate as rural areas, which are covered in vegetation and soil that release heat more quickly. Furthermore, the geometry of a city, with its tall buildings creating urban canyons, traps reflected and re-radiated heat, preventing it from escaping easily to the upper atmosphere. The very structure of our urban spaces is designed, albeit unintentionally, to trap energy and elevate temperatures. Another contributing factor is the waste heat generated by human activity itself. Every car engine, every air conditioning unit, every industrial process, and even every human body releases heat into the environment. In a densely populated city, the combined effect of this waste heat is substantial. It adds another layer of thermal energy to the urban atmosphere, further exacerbating the temperature difference between the city and its surroundings. This is a direct thermal forcing, a constant input of heat that has nothing to do with the greenhouse properties of carbon dioxide, but everything to do with the energy consumption required to sustain modern urban life. It is crucial to distinguish this localized surface-level warming from the concept of global warming. The urban heat island effect is about how we have changed the land, while the greenhouse theory is about how we have changed the air. Many of the temperature sensors used to track global climate trends are located in or near these expanding urban areas. While climate scientists attempt to adjust for this urban bias, the challenge of completely separating the strong localized signal of urban heating from the weaker, more diffuse signal of global greenhouse warming is immense. We are measuring a fever in our cities, but we may be misdiagnosing its primary cause. Now we turn our attention back to the atmosphere and the role of carbon dioxide. As we discussed, carbon dioxide is a greenhouse gas because it absorbs outgoing long-wave radiation. However, it does not absorb all of it. The CO2 molecule is very particular. It primarily absorbs energy in a few narrow bands of the electromagnetic spectrum, with its most powerful absorption band centered at a wavelength of 15 microns. Water vapor, the most dominant greenhouse gas, absorbs energy across a much wider range of wavelengths. This means that CO2 is only capable of trapping heat within these specific limited windows of the spectrum. The existing concentration of CO2 in our atmosphere is already quite effective at doing this job. At its key 15-micron band, the CO2 present in the lower atmosphere is already absorbing nearly all of the radiation that the Earth's surface emits at that specific wavelength. Think of it like putting a blackout curtain over a window. The first curtain blocks almost all the light. If you add a second curtain, it will block the tiny fraction of light that might have leaked through the first one, but its additional effect is minimal. The first curtain has already done most of the work. In physics, this is known as saturation. This saturation effect is a critical concept that is often lost in the public discussion of climate change. The relationship between CO2 concentration and its warming effect is not linear. It is logarithmic. This means that as you add more and more CO2 to the atmosphere, each new addition has a progressively smaller effect on temperature. The first 100 parts per million of CO2 had a very significant warming effect. The next 100 parts per million had a smaller effect, and the next 100 parts per million had an even smaller effect still. The atmosphere is already opaque or saturated in the central part of CO2's main absorption band. Therefore, the idea that more CO2 will continue to trap heat at the same rate is contrary to the fundamental physics of radiative transfer. While additional CO2 can still have a minor warming effect by absorbing energy in the weaker, shoulder parts of its absorption bands, or higher up in the atmosphere where the pressure is lower, its ability to trap heat is severely limited. The heavy lifting of heat absorption in that critical 15-micron window is already being done by the CO2 that is currently in the atmosphere. This physical reality places a strong constraint on how much additional warming can be caused by future increases in CO2 concentrations. The logarithmic nature of carbon dioxide's warming potential is a cornerstone of atmospheric physics, a principle acknowledged even within mainstream climate science, though its implications are often downplayed. This principle of diminishing returns is essential for a rational understanding of the issue. It means we cannot simply draw a straight line and assume that if a certain amount of CO2 caused a certain amount of warming in the past, then doubling that CO2 will cause double the warming in the future. The system simply does not work that way. The Earth's climate is not a simple linear equation. Let us consider the journey from pre-industrial CO2 levels of about 280 parts per million to the current level of over 400 parts per million. This increase of roughly 140 parts per million has been blamed for the warming observed over the last century. However, according to the principle of diminishing returns, the next 140 parts per million increase, which would take us to 560 parts per million, will have a significantly smaller warming effect than the last 140 parts per million. Each successive molecule of CO2 finds it harder and harder to find a packet of energy to intercept, as most of the available energy in its specific absorption bands has already been captured by the molecules already present. This is why the scientific debate often centers on a concept called climate sensitivity, which is the amount of warming expected from a doubling of CO2 concentrations. The estimates for this value vary wildly, which is a clear indication that the science is far from settled. However, even the mainstream estimates do not suggest a catastrophic runaway effect. They suggest a modest temperature increase for a doubling of CO2, an effect that gets smaller with each subsequent doubling. This reality stands in stark contrast to the alarming rhetoric that often portrays CO2 as a runaway control knob for the climate, where each small addition pushes us closer to a tipping point. This physical constraint is a powerful argument against climate alarmism. It suggests that there is a natural ceiling to the warming effect of carbon dioxide, while other feedback mechanisms, such as changes in cloud cover or water vapor, are proposed to amplify CO2's initial warming effect. These feedbacks are themselves highly uncertain and poorly understood. Some feedbacks may even be negative, counteracting the warming. The core physical effect of CO2 itself is limited and becomes progressively weaker. This is a message of moderation and stability, not one of imminent and accelerating catastrophe. The fear of unlimited warming from unlimited CO2 is not grounded in the physics of radiative transfer. One of the greatest sources of confusion in the climate debate is the conflation of two very different phenomena: the localized heating of our urban environments and the theoretical warming of the entire global climate system. As we've discussed, the urban heat island effect is a real, powerful, and easily measurable process. We have built cities that are objectively hotter than the countryside. When we place thermometers in these cities to measure temperature trends over time, they will naturally record a warming trend as the cities grow and become even more effective at trapping heat. This is a measurement of local man-made environmental change. The theory of global warming, on the other hand, posits that an increase in atmospheric CO2 is trapping more heat across the entire planet, warming the oceans, the rural areas, the poles, and the atmosphere in a uniform way. The problem is that our primary method for detecting this global signal, our network of weather stations, is heavily contaminated by the much stronger local signal of urban heating. Many historical temperature records come from stations that were once in rural areas but have since been swallowed by expanding cities and airports. Separating the local heat signal from the global climate signal is an enormous statistical challenge. Consider the narrative we are often presented with. News reports of record-breaking temperatures are almost always centered on specific cities. We hear that New York City just had its hottest July on record, but this is a statement about the temperature within a massive urban heat island. It is not necessarily a statement about the temperature of the entire planet. While climate scientists use complex algorithms to try to adjust the raw data and remove this urban bias, the process is imperfect and subject to assumptions. It is entirely plausible that a significant portion of the global warming reported over the last century is actually a measurement of the growth of our cities. This distinction is not just a matter of scientific nitpicking, it has profound policy implications. If the primary problem is the urban heat island effect, then the solutions are local and practical. They involve planting more trees, using reflective cool roof materials, designing cities with better airflow, and creating more green spaces. These are tangible engineering and urban planning challenges. If, however, the problem is global CO2 emissions, the proposed solutions involve a complete restructuring of the world's energy system. Before we embark on such a monumental and costly transformation, we should be absolutely certain that we have correctly identified the problem and are not mistaking a local fever for a global one. While carbon dioxide has been demonized in the context of climate, in the world of biology, it is revered as the gas of life. CO2 is the essential raw material that plants use for photosynthesis, the process that converts sunlight into chemical energy, forming the base of nearly all food chains on Earth. Without CO2, there would be no plants, and without plants, there would be no animals, including humans. A higher concentration of CO2 in the atmosphere, therefore, is not necessarily a negative development for the planet's biosphere. In fact, a wealth of evidence shows that it is having a profoundly positive effect. This phenomenon is known as the CO2 fertilization effect. For decades, commercial greenhouse operators have been pumping CO2 into their facilities to concentrations of 1,000 parts per million or more because it makes their plants grow faster, larger, and more robust. The same effect is now happening on a global scale. Satellite data over the past several decades has revealed a remarkable trend. The Earth is getting greener. Large areas of the planet, including arid and semi-arid regions, are showing significant increases in foliage, a trend that researchers have largely attributed to the rising levels of atmospheric CO2. One of the most significant benefits of higher CO2 levels is an increase in water use efficiency for plants. Plants breathe through tiny pores on their leaves called stomata. They open these stomata to take in CO2, but when they do, they lose water to the atmosphere through transpiration. When the concentration of CO2 in the air is higher, plants do not need to open their stomata as wide or for as long to get the amount of CO2 they need. This means they lose less water, allowing them to thrive in drier conditions and better withstand periods of drought. This is particularly important for agriculture in water-scarce regions of the world. This greening of the Earth is a crucial yet often ignored part of the CO2 story. It represents a powerful negative feedback that counteracts some of the claimed negative effects of climate change. More robust plant growth can lead to increased food production and a more resilient biosphere. To label CO2 a pollutant is to ignore its fundamental role in sustaining life. It is to look at only one side of a complex ledger. While the climate effects of CO2 are debated and constrained by physics, its benefits to plant life are direct, measurable, and happening right now all across our planet. We have journeyed through a different telling of the climate story, one that challenges the simple narrative of carbon dioxide as a planetary villain. We have seen that the physics of radiation place natural limits on CO2's warming potential, with its effect diminishing as its concentration rises. We have explored how the massive transformation of the Earth's surface, from natural ecosystems to heat-absorbing cities and farmlands, creates a powerful local warming signal that can be easily mistaken for a global climate crisis. And we have recognized CO2's vital role as the food for plants, a role that is currently contributing to a measurable and beneficial greening of our planet. Esteemed scientists like William Happer, a physicist at Princeton University, have long argued that the climate models exaggerating CO2's warming effect are flawed and that the benefits of more CO2 are being ignored. These are not the voices of deniers, but of serious scientists urging a more balanced and empirical approach. They remind us that correlation is not causation, and that we must be careful not to attribute every observed change in our complex and chaotic climate system to a single variable. The focus on CO2 has become an obsession, blinding us to other important factors and to the possibility that the changes we are witnessing are more modest and manageable than we are told. The time has come to step back from the brink of panic and reevaluate our relationship with carbon dioxide. We must learn to distinguish between the tangible, localized environmental problems we create, like the urban heat island effect, and the more abstract, uncertain theories of global climate catastrophe. We should focus on practical solutions that improve our immediate environment, building cooler, greener cities, and practicing more sustainable agriculture. These actions have direct, measurable benefits for human well-being, regardless of one's views on global climate sensitivity. They are solutions grounded in engineering and common sense, not in fear of a speculative future. Ultimately, carbon dioxide is not a pollutant. It is a vital component of our planet's life support system. It is the gas that builds the trees that give us shade and the food that gives us sustenance. While it does play a role in the Earth's thermal balance, that role is constrained by physical laws and accompanied by profound biological benefits. To wage a war on carbon is to wage a war on a fundamental element of life itself. A more rational path forward is one of humility and curiosity, one that respects the complexities of our planet and sees carbon dioxide not as a villain to be vanquished, but as a misunderstood and essential partner in the great enterprise of life on Earth.